Charlie Hitzelberg, I see you now. You are on the bus, on your bus. And I see Ralph has joined us, and Don also, and Atle from Norway.
Hi, guys.
Francois, I say hello, Francois.
Hi.
Who else? You have people from everywhere. Then I see, sorry, I am trying to find new members who join it now. EFF, I don't know who EFF is. Hello.
I'm back.
Hey, yeah, just a new guy. I join once in a while, joining from Canada, Toronto.
You are where, in Canada?
Yeah, Toronto.
Ah, okay, nice. Nice place. And who else has joined it?
Let's see here. Christoph. Christoph just did.
Hello, how are you?
We're good. How about you?
My English is very weak, sorry.
Ah, you should see mine.
Or mine.
See it?
Well, those with English as a second language have a permanent license to butcher English grammar and vocabulary mercilessly.
Well, you know what? You have a second language. I don't. So you're you're better than I am for sure.
Hey, we all speak fluent sarcasm.
There you go.
All right.
Yeah, actually, the lack of having a second language is something that it bothers me as a life experience that I will never have. It just sort of like my brain, yeah, it just is a life experience that I think it's valuable in a sense that my brain is not cluttered with another language, but other than math and fourth and APL and so forth. But at the same time, boy, it's just a big hole in my understanding of an awful lot of existence.
You're never too old, Bob.
Yep. Hey, you're never too old to learn fourth, so.
No, I'd have to move somewhere, yeah, and get a woman friend. That's the way. And maybe move somewhere in Africa.
The thing with the second language is that ideally to learn it properly, you have to go to a country where it is spoken. And that right there expands your worldview and your horizon with a sledgehammer.
Yeah.
It's an experience to see, and even only to see how things are done elsewhere, and probably even more important, see the place where you came from the outside. Talk about a new perspective.
I recommend Colombia. I had a girlfriend down there once. It was really something else. And when we visited Cartagena and Bogota, totally kind of blew me away because I never really been out of the country much.
Oh, and then you go to a Mediterranean or South American environment. Coming from here, that's That's an interesting change.
In Brazil too. So Portuguese would be a good one to learn.
Yep.
One of the advantages of force is you can program multi-language. I speak different languages. As a kid, I learned German at home, and we spoke at home 2 languages, Spanish and German. And when I began programming in force as a young programmer, my programs were in 2 languages, were half in German and half in English. And for example, for a machine, when you control a CNC machine and you write the word emergency, nobody cares of emergency. But if you put this word in German and you put Achtung, then everything will blow away. You know it's something very, very different. You will take care with Achtung.
Wow, that's a good point.
It sounds so
Right.
authoritative.
With the exact
Peter,
pronunciation was.
Mhm.
Peter, a quick question for you. Do I understand correct that your CNC equipment is controlled by some kind of device which runs forth?
Yes, we built our controllers with force. I was an assembler programmer, a macro assembler programmer. We used small micros to send the pulses to the motors and to read the encoders back, etc. And I was in a very difficult, I entered into a very difficult problem with the floating point, and the machines would never come back to the same point. And force resolved my problem. With the integers.
It's interesting because we don't see a lot of real life implementations of forth systems these days. So, with your experience.
I could not understand you. If you close your video and only use audio, probably we can.
Okay. So is my sound better now?
Yes.
Yes.
I want to say I'm kind of excited with your experience because we do not see a lot of real life implementations of forth systems these days. Looks like everybody just puts some numbers on the stack, then summarize them and use dot to print it. But it's probably the same situation like with the Arduino when everyone writes a program to blink the LED on pin 13. But it's so good to know that real forth systems work for.
Can you see my screen?
I can.
Yes.
This is, I wanted to show this to Chuck because he will love to see that. This is Pablo Reda in Argentina. He's a friend of our group, and he produces his own force. He makes a force called R3. Force R3, sorry. And he's using this force actually to send video on a television channel. And he makes an overlay of live images with text automatic. This text comes automatically as publicity over the live channel. So this is a real life application which is running today. So he's developing this, but this is already live. You see here a monitor, a screen here with the text below and information, etc. All this information is produced by force.
was talking to Dimitri a few days ago, and I kind of had an epiphany. I've been thinking about this for the last couple of months. I watched Alex, I forget his last name, but he's the MIT programmer that has the really good interviews. And he had an interview with the top, like, Intel microprocessor developer. And the guy said a couple things that blew my mind in the video. Number one, he said that, you know, they're all designed to run off of, you know, DDR memory, which you only have like 4,000, you know, cells available, and then you have to bank switch. And when bank switch, of course, it's a lot slower. So to get the speed up, he says what they do in the microprocessor is they try to predict where the next jump will be. And he said it's about 97% effective. And then they have this other system that captures errors. That's supposed to catch the error if the jumps to the wrong place. And he said, and the last thing he said that I thought was, it got me really thinking that it's time for Forth to take over again. He said, every 5 years when you're designing microprocessors, you should start with a clean slate, start over. And then the other thing I was thinking was, you know, C is a 60-year-old language, it's 60-year-old technology, right? During the 80s, there was a war between Forth and C for embedded systems, and Forth was actually bigger in embedded systems than C was. But all the academics were pushing C. So C didn't have an interactivity, so they invented Java. C didn't have create does, so they created C++. You know, and all these are really complicated languages. They're huge binaries. My laptop runs Windows 11, and just to start up, it takes 5 gigs of memory to run. 5 gigs.
Sorry to interrupt you, Don. Konstantin, did you see what Pablo is doing?
Yes, I did. Yes, I did. I'm impressed.
Did you understand what he's doing with real-time video? He's capturing video,
Right. Yes.
decompressing video in real time, adding text over it in overlay, and sent to the live broadcast.
Mm-hmm.
And Don said something about the size. This program is only 70K.
70 kilobytes?
70Ks.
Are you kidding?
And today, I give this to another programmer in any other language. And in 70Ks, the guy is not able to make a PDF because the PDF will have 1 megabyte at least.
Fantastic.
Yeah, Hello World is probably 200,000.
200,000, yes. Hello World in C++.
And partially my question to Chuck is about that today.
Yeah, talking about force systems and how they are presented and being used. I have been to an academic workshop of people who write compilers or do research into writing compilers. And I made 2 very important observations. One thing is they don't have a heck of an idea how the force system works and how simple things can be. Secondly, they are now not really content with what they have and the approaches they have. So the past approach, in their view, They call it the semantic approach, where you define the semantics of a language and then you build a mostly very complex compiler to turn this into machine code. So there is a second tendency which started with APL and Force and Prolog, which is called the dictionary-based approach. I mean, where you just define words and put them into a dictionary without taking much note of semantics. And one of the interesting research results is that both systems allow to do the same things. So there is no real benefit in the semantic approach because everything that the semantic approach does can be done with a dictionary-based approach. And they were also asking for other features that such a new programming language should be able to fulfill. And when I read, I mean, 4 or 5 features that were termed matter of research, unsolved problems that are needed. And I could just write down how Force does these things. So with Force, we already have the language that they now want to have. But of course, they would have to admit that it has been there for a long time already and not invented by them. So next year, I'm going to visit them again, and I will present Poor Man's compilation, how Force treats its source code.
The comma compiler.
Coming from the APL world, and actually just the last couple of days, I've actually had to go back to my accounts in K, because my accounting in Cozy was not up to dealing with things. But one of the real APL, don't give it any break on the syntax. The syntax is too clever by far. K sort of simplifies that some, but still RPN is such a brilliant simplicity. I mean, it is so much easier and more flexible to write things than in the APL syntax, which is sort of backwards, and then goes and mixes syntax and semantics together. No, that's again, it's as Chuck said, I have a quote on my page. Is I've gone to some lengths to simplify, and boy, the simple is so powerful.
Now
So
that you mentioned that, oh my God, I had to compile some C++ code at work for a project, and the compiler, after a recent upgrade, didn't like it. Bombed in a template, in an application of a template to a template which accepted some form of pointer. So I read through this thing. I read through it again. It did not make any sense to me. So Stack Exchange, Google, yeah, point at something. I look at that thing and it's like, this is just an invocation of something. So why would on earth would you package that into a template of a template? Turns out the template around something with a pointer was there so that you could invoke a function that returns something and ignore the result. So that is roundabout the same as in good old C, passing a void star, or in Forth, just drop the damn result from the value stack, from the data stack. And we have almost a half of a line on the screen of gobbledygook in C++ just to ignore a result. Good morning, something is wrong here.
Well, you know, Forth is really not a language, it's a virtual machine. And I remember in one of Chuck's talks many decades ago, I don't remember which one it was, he said, I discovered Forth. And that really hit me, because it means that this is the way that you design a microprocessor. And when he was writing, I think he was talking about the Pikes Peak assembly code, he started noticing that he was like, it was more efficient to use the stack to store things, and it was more efficient to use go subs instead of jumps, and the code became more readable. And correct me if I'm wrong, Chuck. But and you know, and then it was the only language that I know of that was actually committed to silicon, because it describes hardware. It describes the way a microprocessor works. And when you look under the hood, if you look at Dr. Ting's code where he was using JavaScript, it's most of the byte functions are, you know, are Forth, you know, dupe, drop, swap, you know, and you know, it's time to get back, you know, keep it simple, stupid. Computers are bogged down with software that is so complicated you can't possibly debug it anymore. And I'm just waiting for the day when everything just like crashes. Some you know, they come out with a new compiler and then nothing works anymore.
Wait, we're already there. You install a new compiler, everything crashes. Or in your case, you install Windows 11 and everything crashes.
Yep. I was having some trouble with Windows 10. I switched to Linux like in early 2000s, but my last job was all Windows, and I left my laptop in Windows. I still need to do a dual boot, because I keep cussing at my computer running Windows 11. Linux is pretty good, actually. Still more complicated than OS needs to be, but it's reliable.
I don't know if you heard me rant about this earlier, so we'll keep this short, but I'm at a point that I'm stating Windows has downgraded your really, really expensive laptop to become a terminal, because the important stuff happens elsewhere, and this Windows terminal is just there to get you a connection to that very point. So in other words, if I want to do Forth, it's going to happen on a Pi or some other target device that's hanging off a Linux box. And the sole purpose of the Windows system is connect me to that little stinker. And it does not matter where in the world I am. I want to be able to code Forth at home while hauling down 100+ miles per hour on a German Autobahn, on the passenger seat, of course. And I want to be able to do so without dropping the connection once. That's what laptops these days have to be able to do. For everything else, I have a nice little embedded mainframe at home for the important things in life.
Cornelius, I think I have a machine for you. So Dimitri and I have been pretty busy on personal things the last 4 months. So we have been working on Core 1, and the outer interpreter works fantastic, and it's all written in System Verilog. So he and I came to an agreement. He's going to finish up the source code on Core 1 by Christmas, and I'm switching to developing a dev board. Yeah, I'm an electrical engineer, by Christmas. And we're going to put an ESP32 and an FPGA on a board with a display, and it's going to be solar powered. It'll have a battery and a solar cell to power it. So it's going to be an eternal computer. It never turns off. And Chuck, well, I'm going to send you one. That's your Christmas present. But you'll have the Core 1 running Forth in Silicon, and then you'll also have the ESP Brad's and Dr. Ting's Forth. So you'll have the Bluetooth, and you'll have Wi-Fi built in, you know, and ADCs, stuff like that on the ESP32, and then the Core 1. You're going to actually have up to about 5 or 6 Core 1s can be running in Fabric at the same time, concurrently. So I'm not sure what kind of application you would need for all that horsepower, you know, because the Core 1 should be running at 100 megahertz plus each one of the, and the true 32-bit cores. And there would be no memory limitations. I'm going to put SRAM on the outside and flash. So the flash would be like your disk. I'll also put an SD disk. So that's your hard drive. So it's the first one I'm going to do is an embedded. I'm going to use a small screen, but next year I like the idea of building a tablet. So I'll use like a 10-inch screen and put even more memory. I like the new non-volatile memory. What's it called? FEM, I think it is.
FRAM,
anyway.
ferroelectric memory.
Yeah,
Not really tiny little cores, but the behavior is the same in as much reads are destructive, so you have to write it back. The only caveat is that you have to pulse chip select. There are designs out there with few chips. They ground chip select the whole time and just do this with output enable and write enable. An FRAM will not do that. An SRAM, static, like 62, 64 and friends, they will work that way. An FRAM needs the falling flank of the chip select to cache the address to write back data that you just read.
Okay.
And
Are you saying that FRAM is starting to get a real market?
Oh, heck, as far as I'm concerned, it has one. The fact is only there are folks who haven't realized that yet. If you have memory that looks like your regular memory and you pull power, and the contents is still there once you power it back on, and you do not have to diddle around with SD and all the API to SD and all these extra complications. You continue where you leave off, which in a fourth environment means you get your machine with one set of configuration code in it, and everything you add to it magically stays after you lose power, and it's still there. Heck yeah.
Yeah, Ramtron, which is really the creator of
yes,
yeah, is here on the north side of Colorado Springs. There's even Ramtron Drive, and I think they're now owned by Cirrus, perhaps. But I invested in them back in my New York days, my Manhattan days. So I invested in them probably in the mid 90s, and it's one of those things where the tech really did seem fantastic, but boy, I mean, it has been a lifetime, or it's been. I mean, that was like I say, at least 25, 30 years ago. It was one of those investments that my tendency to be attracted by the technology. Having technology and making money are somewhat correlated, but the one does not imply the other.
Yeah. This FRAM stuff, once you have that under control, it's fantastic. I use that to easily test my EEPROM burner. Okay, EEPROM, and it doesn't burn it right. There's no high voltage of the 12 or 21 or 25 volts in there, because it had to be simple. But I tested my reader writer first with SRAM, simply because it has the same pinout and it's faster, then with FRAM, and just because, and then eventually with EEPROMs.
Flash. I mean, is the you know, Flash came along, and that, if you will, is delayed enormously. FRAM, I think partly because of the density. They didn't have the density of memory that Flash provided.
Yeah, but quite frankly, what did we just hear? Like a video feed system for a TV station in 70K? So why exactly would I need terabytes or gigabytes of space if I can cram my stuff into something that elsewhere qualifies as background noise? Heck, you can get a chip, an FRAM chip, something that's through hole that you can, as an elderly person, crap, I just dated myself, still solder, even if your hands are not that stable and your eyesight is on the back end of something, you can still solder that. One of these little chips is 32K, 2 of them or 4 of them, you can still fit them on a very small board with all the driver and a CPU and other stuff. And you don't need a battery, and you do not need all that extra overhead to drive an SD card. And friends, it's for the ultimately lazy. I love it.
Okay, I see many new friends in the have joined. I see Brad Rodriguez. I see Shi Liu. Sorry, Shi Liu, I did not recognize you in Taiwan. Do you want to say some words to Chuck for his birthday, or any questions, etc.?
Bless you.
Shi Liu, Professor Shi Liu Shen.
Hi, Peter.
Hello.
Hi. Happy birthday to Chuck Moore. And yeah, today's Chinese Lunar Festival. So wish everybody have a good day. Okay, thanks.
Yeah, happy birthday, Chuck. Another day younger.
Oh, come on. We never turn older than 28.
Yeah, my birthday's on the 11th, September 11th. Oh, tomorrow. Another day younger. That's what I tell people on LinkedIn. Oh, happy birthday, Don. Another day younger. That's my response.
Growing
That's not going to
old,
work forever, though.
Growing old is inevitable. Growing up, on the other hand, entirely optional.
Nah, I don't want to grow up.
Nah.
No way.
Then you have to give away your toys.
I see Alvaro from Rio de Janeiro has joined it, and Rob Jute from Australia. Hi, Rob. Jason from Malaysia, and Christian Hinze from Canada. Hello, Christian. Many people from all places.
Uh-huh. Gotta love an international community.
Yeah, it's impressive.
Mm-hmm.
Yeah, we have to go all over the world to be able to find 40 people.
Now.
Yeah, but think about it. You are
The top
able.
40 though.
But think about it. You are able to go all over the world to find these 40 people
In your home.
Sorry, Peter. I have to report this prank, this joke that I read 20 years ago. That some people were ashamed that drug dealers and smugglers are free to go and go. I mean that the drug dealers go to jail, and still the Ford programmers go free.
I don't know if everyone knows the Hanna-Barbera cartoon. I'm drawing a blank now. George Jetson. And George Jetson was born in 2022. So I think we beat the video phone by 40 some years. So that's pretty good.
And his is probably a fourth phone.
You guys, as programmers, had the chance to stay home. As a technician, I always had to get there.
I see also Michel Jean from Canada. Hello, Michel.
Hello.
And Wolf Wechiert also. Hello, Wolf.
Hello.
Hallo, hallo Wolf, es mag für dich sehr, it may be a big surprise for you, but I came to the decision that bytes are not as useless as I told people for years and years and years, but if you have substantial packages like the IP stack of protocols, you better have a byte addressable processor, or else you cannot use any of those large libraries. And therefore, microcore now allows you to have byte addressing. If you have a 16 or 32-bit architecture, you can also select byte addressing. And so in that respect, then it will be compatible to the rest of the world.
Which, by the way, you will need once you have a phone that runs forth. A lot of the messaging in phone systems, a lot of it is byte-based. So just saying everything is n instances or n bytes long, 2, 4, 8, and so on and so forth, because we have a CPU that is with a data path that's so wide, no protocols, unfortunately, don't work this way. Protocols, IP and otherwise, you name it, it's byte bingo. And within the bytes, it's bit bingo. So your bit operations better be snappy.
So that being said, what do you guys think about, the Core 1's a 32-bit computer. It's 32 bits wide. Thoughts on doing better byte manipulation in a 32-bit environment, 30-bit, because we can add opcodes to do anything, right? Thoughts?
No, you just need cfetch and word fetch and the usual fetch, which is a full, assuming 32 bits cell. That's it. That's all you need.
I agree.
But then you're throwing away the 24 bits if you just implement cfetch and cstore.
No, I'm not throwing it away. I mean, but if you have a 24-bit processor, then you cannot use byte addressing, period.
Well, you could,
If
but
you
at a
want
penalty.
byte addressing, you have the selection of 16, 32-bit or 64-bit word widths.
Maybe you have a register that's that looks into the memory in a byte format, and then you have a separate always statement, separate process that if you want to increment through, let's just say you want to increment through 4 bytes, but they're all in 32 bits, then it would do the math with cfetch and cstore to be able to utilize all 4 bytes in the 32-bit data width. That's what I'm getting at.
If you have your processor in an FPGA, you just bake your instruction that does exactly what you say in one instruction. So that doesn't need byte addressing of the memory. It's a special sort of plus store.
Yeah, we're going to get the whole thing working before I worry about the byte stuff, but that is something in the back of my mind. I don't want to throw away 24 bits, just because the data width is 32, and you want to implement cfetch and cstore, and you increment the memory pointer, and you go to the next 32. So basically, we need a.
No, wait a second. That's not how byte addressing works. I mean, for byte addressing, you take the least significant bits of the address, and that is the address of the byte you are accessing. So in a 32-bit system, you have 2 bits at the end that tells you whether you want byte 0, 1, 2, or 3 before you go to the next cell. I mean, this is how force works on the IBM PC.
If you have an external 32-bit chip, right? So it's hardware 32 bits.
What do you mean by a hardware 32-bit chip? What chip?
Well, if you have a 32-bit wide data bus going out of the FPGA into a 32-bit SRAM. Oh, I see what you mean. Okay, I see what you mean.
Yeah, then the 32-bit SRAM, if it exists at all in a large package, you do have then 4 byte enable inputs where you can enable byte 0, 1, 2, or 3. And this is how it works on writing. On reading, you read everything, and then you just barrel shift it into the least significant position. But on writes, you have individual byte enables.
All right, thanks. So Chuck, what have you been up to? Are you living off the grid? Oh, you're muted. You're muted.
He is? No, he's not.
Oh,
His
his
sound
volume
is
is
not.
too low.
I don't think his sound is working. Can't hear you.
Can't hear
You're
you.
just very soft, Chuck.
Huh.
No, your microphone doesn't work, Chuck.
I can hear you very, very, very faintly.
There's got to be an input volume on that mic.
Probably Windows. It forgot how to manage a microphone. But we're gonna have to do lip reading.
Oh, please.
We still don't hear you, Chuck.
This is not a problem of Windows, Don. This is color force. It's a bug in color force.
Oh, is it? Yeah. It wouldn't surprise me if he's doing that.
this Zoom technology is fantastic, but I have also a lot of trouble with microphones. And when a computer detects that I plug the earphones, it gets messy. And
that's actually from these history of Zoom conferences that I've hosted and participated in, the most prevalent problem, reoccurring problem, is audio, and not listening, but the mic. The mic, the video is great, and they can hear us just fine, and then they start talking and it's crickets. And in quite a few cases, it's some hidden volume controlled setting for the mic that is separate from everything else. And I must admit, I probably got lucky so far because I've never encountered that, but then I've yet to find this volume control for the mic.
Peter dictates to his computer. He prefers it to typing and particularly prefers it to pen and paper.
Whatever you did, Chuck, you made it better, but it's not quite high enough. We can just barely hear you now. But you did make it better.
Peter dictates to his computer. He prefers it to typing and particularly prefers it to pen and paper.
Uh-huh.
The microphone is ready to use with his computer.
Well, we can hear you barely, but we can hear you now.
Yeah, it's way better. It's not perfect, but it's way better than before.
So are you living off the grid? Where do you live? Uh-oh. Went quiet again.
Lose connection, maybe?
The reason I'm asking that is I bought 20 acres here in Florida, a very rural area in the middle of nowhere, and we're in the process of building a log home on the 20 acres. And we should be start assembly of the log home in January, February timeframe. So next summer, I'll be broadcasting from the middle of nowhere in my totally off-grid, self-sustainable, we're calling it Stargazer Ranch. See, this is actually a picture from the night sky out there.
Damn.
The stars are amazing. There's the nearest town is like 15 miles away.
That's actually decent. It's not too far out for a trip to the grocery store.
That's right. Yeah. So we're experimenting with planting our own food right now. We've bought apple trees and citrus trees, even an olive tree. We're my fiance Cherie, she's at her house here in Jax. We have our backyard full of plants and stuff and trees. We have a dozen trees back there of different things, and we're going to be building a pond and putting these trees, fruit trees and things. And the other thing was I did a web search on what is the most profitable crop per acre. Bamboo.
Really?
Bamboo. So we have 2 acres that we're going to build a bamboo forest in using Moso, M-O-S-O. Bamboo is a construction bamboo. And we're if you go on Amazon, put in bamboo poles, and you'll be amazed. You get 4 like 3-inch poles for $150. So this bamboo grows. It's actually a grass, and it grows like 24 feet in a year or some crazy thing. And every year it does it again. So when you chop, you go and thin your forest and sell the thinned, sell the poles. Then the next year you have new poles, and you can get up to $5,000 per acre income from a bamboo forest.
Say, Don, I always thought the most profitable crop was hops myself.
Yeah, I like the bamboo though better. You go out there, and start a little fire, right?
Yeah, but I guess we should all say congratulations to Don, and it's been nice knowing you. It sounds like he's going to be very, very busy. He won't make the next couple of meetings.
Oh no. I plan on getting Starlink, and we do have Verizon. Verizon's strong out there.
Okay.
So you'll see me.
As long as you don't get arrested for your side, for your moonshine business on the side, we're all going to be good, right?
My next door neighbor here is from Virginia, and he has he when he goes up there and visits his family, they all make moonshine, and he's got this stuff called white lightning. It's like,
oh yeah,
75% alcohol. Oh my! But you know what? You don't get a hangover with it.
Nope. There's
be careful. You gotta test it with a flame before you drink it.
You don't want to get a flame anywhere near it. You'd explode.
No kidding. At room temperature, if it's north of 52% by volume, it burns.
Well, most rocket fuel, ethanol rocket fuel is at 75%. Apparently, they don't use 100% because that increases the combustion temperature without giving you a lot better thrust. So there's no point. It makes the engineering more difficult.
Yep. With that higher percentage, you will literally burn the rocket's butt off.
There are some good YouTubes, excellent YouTubes at an engineering level on modern rocketry. And one of the interesting things is a comparison. Actually, one of the interesting ones, these are on my daily blog now, but the links, but it's an engineering level comparison between all of the rocket engines. And one of the interesting things is the fact that SpaceX, Musk is simply in another generation. It's free market versus the state that you're seeing in the ossification of the NASA model. It costs $1 billion per flight. And Musk is going for essentially cost of fuel. And the fuel is methane, which is CH4. So actually the volume of the liquid methane and the liquid oxygen are approximately the same. And so I don't know if they use ethanol or ethane. No, you said ethanol. Right, in any case, definitely there's some really, the guy's great. He even, as a matter of fact, has a little bit of a conversation with Musk, where it is essentially an engineer-to-engineer conversation. So Everyday Astronaut is the name.
I love that guy. Chuck, I just had an idea. Unplug your headset and try talking to us. That'll switch it to the microphone in your computer. Are you using a laptop computer?
This one. Other than the
There you
camera.
go. That's it. You got it.
I disabled all the other apps. So I was getting some kind of crosstalk.
Oh, now you're great.
I'm glad to participate.
So obviously I'm going off grid. So are you off grid?
Not really, no. I'm 5 miles from town.
Okay.
And 25 miles from Walmart.
Yeah.
Okay.
What state is that?
Huh.
What state?
Nevada.
Okay. Is that northern Nevada?
Northern Nevada, high desert.
Nice.
Yeah, beautiful area. I was kind of, when I was thinking of living off grid, I was looking at Wyoming, The Northeast Nevada is, remember, I'm a gold prospector. I love to go out and look for gold. Northeast Nevada, what's it called? That area, but there's a humongous open pit gold mine up there. Starts with a J, I think. The name of the area.
There's lots of gold mines. Now there's going to be lithium mines.
Yeah, but Teller County, actually, the county seat, has mountaintop gold mining. It's there, Cripple Creek. The county is independent, actually, because all the gold miners essentially went and separated themselves from the lowlands. So you have a number of these counties in Colorado, which are very small, but they were gold rush counties. And the locals essentially said, you know, screw it, we'll administer ourselves, you know.
A partner in mine, we were trying to start a gold equipment company, and we developed a thing called the fiber washer that uses screen classification and extreme vibration, and you could without water you can separate fine gold out of dry material, and we sold about 50 of them, but we lost like $200 for each sale. So it wasn't a very business.
I think it's Newmont, I think, operates the thing now. It's always these mergers and so forth. But yeah, they process a tremendous amount of dirt to go and get, and so they're always looking at, I mean, if gold fell below maybe $1,200 per ounce, whatever the hell unit it is, then, you know, they would, you know, they're breaking even on the cost of getting it out. But the mine's been producing for 120 years. So it's on the side, one part of this off the side of Pikes Peak. It's around the other side of Pikes Peak from where I am. But there's one area, I don't know what the geology of it is that makes it any different than any of the other sides of Pikes Peak. But, you know, over there, there's the gold. But yeah, the whole thing of rare earths, though, that's there's some of that west of here. Yeah, US Molybdenum or something company. But anyway, dealing with the corrupt government in the United States at this point in time is a real issue. These eco-fascists that got their buddy capitalism, John Stossel's word, crony capitalism, which is the classic definition of of fascism. But man, the corruption in the United States, it's world-leading corruption.
Okay, I have some questions for Chuck that many of our friends posted on the Force 2020 group. I share my screen here, and I have a question. Not everybody is in the meeting today, but Travis is in the meeting, and his question was, what motivated you to get into going from creating Force software environments to creating hardware for running Force?
That's a good question. And I've debated it myself. It might have been a mistake, since the Force hardware has not been nearly as successful as the Force software. But basically, I was tired of trying to cope with badly designed hardware. The Force I was working with at the time were real time. interfacing with robots, interfacing with communications. And the interfaces were terrible. I remember one case in which I was talking on a serial line to a mainframe. And I got my end of the serial line up in an hour. And it took a week for the guys at the other end of the wire to communicate. And that got so frustrating, I just said, like, design the hardware too. And it took 2 or 3 tries before I got the right hardware. But the Green Array's chip is the right hardware.
You know, we took a note out of your playbook there. When we designed Core 1, we did it using a primarily combinational logic. So, you know, you talk about how the signal propagates, it's not clocked through the chip.
Right.
We do the same thing in Core 1.
Sounds good.
You know, for each individual instruction, obviously, when you're, you know, incrementing memory and stuff, you have state switches, but the opcodes are actually combinational.
Well, you only need 5 bits of opcode.
Yep. The other thing is you have to see this in the background of the time when all this came up. Because back when we're coming up against a couple of hard limits, coming from the 8 to the 16-bit processors, where all of a sudden there was more demand for processing power. But until we got to the point with prefetching deep pipes or deep execution pipes and all that stuff, the other route was RISC CPUs. Small reduced instruction set, short paths, fast hardware, fast clocks. And fourth lends itself to that. Because you have simple instructions, you have, if you implement it, your return stack is hardware. Your data stack is hardware. And your main memory, well, is hardware. And they're all distinct. You have multiple databases, which got us to the NUVIX, which got us to the RTXs. And the RTXs, if I remember correctly, 6 of them put a lander on a comet. Try to do that with complex, highly integrated Intel gear, where one alpha particle through the wrong spot of the CPU renders the whole damn thing inoperable.
May I share my screen and show you the RTX space applications?
Please.
So this is a web page. So I humbly disagree with you a little bit, Chuck, because your RTX chips were very popular in space and they're still being used in space. But here's some missions. So here's Baja Technology, launched in 2000, controller for extreme ultraviolet instrument, Rosetta. There's just an enormous amount of applications in space. Ball Aerospace has used your RTX a lot. A lot. Look at that. Look at all these different missions. Caltech.
But I'm looking at the dates. This was 20 years ago.
So, yeah, I get that. Let's go down to the end here if they have any other dates here.
This listing, Don, was on the NASA site until year 2000 when they took their off the grid or offline.
So my last job, you know, I designed the computer, an FPGA-based computer for Archinaut One, which I've talked about many times. And I often, because I was designing the hardware, you know, I wasn't. All of our programmers were C programmers, so I chose the RISC-V, and so that they'd have a C compiler. But I often, you know, when I'm designing the hardware, I'm going, man, if I just put a 4th core on here, you know, I could put 6 4th cores on here, one for communications, one for machine control, and the key thing in space is they can't use modern microprocessors because the geometry, they're down to what, 5 or 7 nanometers, going to 4, and the problem is a particle in space will obliterate the transistor because it's too small. And so FPGAs are like 16, 24 nanometer. So they're built, their cells are so large that even if they get struck, it doesn't completely damage the transistor. And so
Yeah.
FPGAs are very, very popular. You get the most processing power out of an FPGA, and also it's a parallel machine. So you know, I know Dr. Ting told me 10 years, you know, in 2010, Goddard hired him to write a 4th application. So I don't know what the program was, but I think they're still using the RTX. It's one of the faster processors out there. There's another one called the Spark, and it's 50 or 100 megahertz. You know, not very fast. I'm working, I have a new side gig where I'm the principal investigator for space avionics on a NASA SBIR for a tiny startup. And I don't know, we'll see. I think I'm keeping my fingers in the space business. That's not I got an embedded systems job locally here in Jax that's paying me more than the space guys were paying me. But it's IoT, you know, it's so low tech. But, you know, it's a great check, and it's helping me pay for my off the grid. But I do want to, you know, stay in space avionics, and I want to come out with a 4th computer, you know, over the next couple of years. This company that I'm working with, if they get a phase 2, then I'd probably be hired on permanently, and then you know, come out with an FPGA based, you know, 4th system like around Core 1, and have, you know, we could put basically for $1 per core, you know, you can, that's how much it costs to put in a Core 1 in an FPGA. So a $30 FPGA can hold 30 cores, as a kind of a rough example.
The other problem that you have in space is this. I mean, okay, one particle, one little bit of electricity takes out your CPU is your first thing. Second thing, the more complex a CPU becomes, microcode and all, speculative execution for stuff beyond a branch, before you know if you can take the branch or not. This complexity gets in the way of completely and totally verifying that your CPU is correct, that under all possible circumstances, all imaginable possible circumstances and then some, it will always do the thing it does. We had a couple of interesting side channel attacks, timing execution attacks on CPU that could be used to read keys, encryption keys out of memory. Now, if you get something like that, and it happens in space, where you do not have the means to easily download a patch and fix that thing, if after something happens, you may I mean, you might not even get the chance because your device just got fried because you had a bug that you didn't find in system test. That means your very, very, very expensive satellite is now a glorified doorstopper for the next satellite that's going to crash into it. You just deployed space junk, a lot of it, and it was expensive. You cannot afford a too complex design because A, the hardware might not be space compatible and you do not have the time to validate this thing enough so that it will still work at the end or maybe even beyond its life expectancy. These Voyager probes, they are still operating because they're low tech. If they were using anything you can get off the shelf these days, really fast, really snappy, and we have no idea what's in it at the end of the day, these things would be toast before they got to Jupiter.
So one of the things that I did thinking about this problem, so they have what they call TMR, and that's triple module redundancy. And the space shuttle first introduced it. They had 3 8-bit computers that were voting on how to control the spacecraft, and so it would take 2 out of 3. 2 out of 3 would work, and it'd reset the third processor that was not giving the correct answer. So what I was thinking is you put three core ones, and then you have a triple redundancy circuit also that takes so you feed the 3 core ones the exact same opcode, and then it flows through, and then this always statement compares those, and if there's 2 out of 3, it'll go with that, and it'll do a reset on the core or do something to mitigate that.
Yeah, but you've still got a single point of failure in the voting
mechanism
circuitry.
But you TMR that too.
You're better off with a simple computer with redundant computers and software negotiation.
So how would you implement it in a single FPGA?
Multiple computers communicating with one another and software comparisons. You don't need to compare the operation of the computers. You only need to compare the results.
Yep.
Right.
And the results are most easily compared with software.
So the software would be an always statement.
Yeah.
Yeah, that's what I was saying.
Because
and then
a voting circuit is complex. It's as complex as the computer that you're trying to protect. And with 3 computers, well, with 3 complex computers, you're finished. With 3 simple computers, you got a chance.
Yep.
And there's nothing magic about 3. They're cheap. You may as well have 6.
Oh, now that you say that, I know of a couple of, I know at least one installation used to store liquefied natural gas for emergency situations, like we have in Germany right now, because gas and stuff from Russia. These guys deploy for each task or each set of tasks at hand, they deploy 6 PLCs. 6 of them, they implement exactly that concept. And they're still there. And I saw them for the first time in the early 90s after the wall came down.
The other thing you want, and this is something the shuttle had, you want different software on each computer. There's no advantage to running multiple copies of the same software. Forth is easy to program. You put multiple teams on it, get multiple solutions, and then compare the results.
Oh, that's a great idea.
Yes, because that way, if one of these things has a hidden error, the other version will hopefully still do the trick, and you're still alive. You can't afford failure. Failure will happen. Question is not if, but rather how soon and how bad it's gonna be. So
yeah, the Argonaut 1 mission is 74 mil, and 1 bit flip and it's toast.
There's the Apollo 11 or Apollo, which was the moon, the lander, was it Apollo 9, 11. Anyway, the existential need to not fail sort of has contributed to COSI. It's their design principle number 3, I think it was restart on failure. And on the way down to the moon, their computer, one of the lessons was one of the design rule number 1 is work on a high level. And that's why I come from APL, why I've done APL in open force. Except simplified, far simplified several generations from the original APL. But in any case, so it's work at high level, and the little minimal like computer that they had in 68 or whatever, they implemented matrix algebra, because of course they were continually doing geometric computations on their way down to the surface and so forth. So that was their design principle number 1. But design principle number 3 was restart on failure. And one of the problems in COSI is that there are bugs in it, and some of them are in my code and some of them are not. And I just had to go out to and make the loop out in DOS restart on failure. I was putting all this time into trying to understand the triggering mechanism and the throw and catch mechanism. Screw it. Just when it fails, I mean, I'm constantly, every time you hit an execution in COSI, it does a save of the environment before it executes. And so you can restart. And that's one of the other things. But Apollo, there's a great YouTube on just the absolute brilliance of the computer on the lander, on the lunar lander.
Or you can restart if you can afford it, but if restart's going to take seconds or minutes.
Oh, yeah, this is one of the things. Yeah, minimizing that so you have checkpoints. You save checkpoints. But the fact is the computer was running at like 95% of capacity, just going and doing the computations that were necessary on the way to the surface. But there were some diagnostic programs that could be run, or ones that gave you more information. And Buzz Aldrin went and asked for this more complex output, whatever, information, and it overloaded the computer by about 5%. So after a certain amount of time, the computer failed. And this is on the way to the surface. And it happened twice that he did it. And then they realized, oh, damn, hey, I can't run these things. And so it was, but the restart on failure, but it is an awful lot about saving your state so you can return to that state very efficient.
Well, that's where FRAM comes in. The world has changed. You don't need to do that.
So you're saying it's essentially just constant, right? You're saving your state.
Yep.
That's fantastic. That's definitely then. It'd be very interesting to see Ephraim finally really have a substantial market. Because
I'm going to put it on the Core 1 dev board. Experiment with it.
Please do. It's fun stuff. It's cool. If I can play with it, then anybody can. If I can talk to this thing, and I'm a software person, if I can do this with a self-cooked board, then anybody can. The most. It's cool.
It's so bizarre going and having invested in this company back in meeting the people who were starting the company and being suckered by their presentation. I think there's some Australians involved, but they did buy me a really nice meal one time when we happened to both be in Chicago at the same time. So, but to go and see Ephraim becoming a real thing, my God, some of these things can take a lifetime to actually have succeed. Yeah.
Let me take a poll, and Chuck, I want you to chime in on this. So I'm designing this dev board. What kind of stuff would you like to see in this dev board? So basically, you're going to have an ESP32 and an FPGA. So the FPGA is a clean block. You don't even have to put Core 1 in it. You could put Klaus's machine in it if you want to, or you could put Dr. Ting's in it. So what kind of peripherals would you like to see in a fourth dev board?
USB.
Okay.
Yep.
And internet.
Internet's going to be covered by the ESP32. You have Wi-Fi and Bluetooth. Because you're going to have an ESP32 coprocessor.
Yeah, those are the things I'm missing on my PC. I can't get access to USB without going through an incredible hassle.
Yeah.
And I've never figured out how to get onto internet for the same reason.
Interfacing with the internet is absolutely the most crucial problem. Exchanging this buggy IUP GUI with just simply a web interface is absolutely, I'll offer a prize, to go and spend a weekend getting it done. I know people like Brad Nelson. I mean, no, I think that, and I think Dimitri perhaps knows how to go and interface with the web. And it's like, I've even got some of this vocabulary, I just don't know how to do it. But the interface should be sockets. I guess sockets are really the defining interface. Is that correct?
Peter Forth and Brad and many others on this call have been doing some pretty cool stuff with the ESP32 Forth and the internet. And so all that stuff, you're going to be able to download that.
I essentially want a WYSIWYG, continue, interfacing, give me the HTML and, I'll deal with it. But how do I, and the thing is, I guess that the socket is really the thing that goes from your process to the outside world. Is that correct? I mean, that shows you the naivete of, but anyway, like I said, I know it's a small problem.
So Bob, you can start today. Go buy, go on the 42020 group, buy the board.
No. I'll put it out as a prize, and somebody who wants to work with me and get it done. But I mean, it really, then Cozy becomes an app on the web. And just with but essentially need a WYSIWYG interface to, giving me, because again, parsing, I mean, Cozy is a language of lists. And so converting HTML, just splitting it on all the tags, you have essentially, I guess it's pretty equivalent to XML, but that's just, so you've got the whole vocabulary for dealing with any structures like that.
So they're doing that today. I mean, Peter, why don't you talk about the Wi-Fi stuff? You guys are running in a Chrome browser. You guys are running this ESP port. You want to talk about that?
I would like to continue with the questions of the group, and later on, and Bob, if you like, we continue like a Force Cafe and keep talking about Bob's cozy and that stuff. But I was amazed all my life, and I think this is the most interesting application of force I ever imagined. I think this must be something for Chuck amazing, that he was able to create a language that was on board of these space probes. And this is the lander on the farthest world mankind arrived. This is Titan, and you see Saturn here. And when I see these images, I try it. I think Chuck is a poet also, not only a programmer, and he must have so much, I don't know, but this makes me wonder, what is your opinion about Chuck? If you feel, you must feel blessed for having this, for having the idea of force, and someday force goes there and lands. I can't tell you. I feel this must be fantastic for you.
It is very satisfying that on two levels. One, that I was able to do it and the people picked it up and ran with it. And second, that it was simple. It wasn't a complex solution. It wasn't an elaborate development. It was carving simplicity out of complexity that made it work. And that's the thing I'm proudest of.
Look at these numbers, guys. 2.2 billion miles. Wow. 240 orbits. And it kept going. It kept going and going. And it took over a decade to go there, to arrive. It was traveling, I think, 12 years or so to arrive there. At a fantastic speed. It was at the speed of, I don't know if 10 times of a bullet, but something like that. 10 moons discovered. And did these people contact you, Chuck, or did you receive any mention from for your force from NASA or ESA?
No.
No?
It's the technical details are never very popular. And the popular press is impressed by those numbers, but not what lies behind them. And in fact, what lies behind them isn't easily available anyway. It does not get documented.
Well, I have many pictures. This is Mercury also. I think Force had participation in a Mercury mission because of the magnetometers. These magnetometers from Caltech were everywhere in the solar system.
Oh.
And green arrays here, mentioning also Harris RTX. And well, this is the most, for my interest, this is one of the most interesting applications of force. And the other one, this Rosetta mission, the lander here on. Phyla.
I didn't know yet used fourth.
Yes, the Phyla had 6 fourth CPUs from RTX developed by the ESA, by the European Space Agency. And again, it was a record because nowhere before mankind could imagine to land on a comet. A comet is a very, very speedy guy and a small rock. So you need to.
Space is a good environment for fourth because it is resource constrained. On Earth, you can have as big a computer as you want, but in space, size is a feature. And in the future, I think redundancy is going to be important because as soon as we get humans out there running the spacecraft, it's going to be very important it keeps working. And a lot of science fiction stories deal with hardware failures. And that doesn't need to happen.
Oh, wow.
Yeah, on the Argonaut 1, we had a RISC-V, and it took, and it probably has to do with, we were using an RTG4 FPGA, which is an older technology, you know, very large feature set, but it used like 10,000 LUTs. Now, people in this forum have said, oh, well, you can get a RISC-V in 800 LUTs. Well, okay, yeah, on a modern FPGA, but these are space rated. And, you know, you could put 10 32-bit fourth computers in the same place, in the same space as the RISC-V. So I just can't imagine that we can't get fourth back into space because it just, you know, it's an order of magnitude better solution than C running on a, you know, a C-based core.
Yes, but the problem with FPGAs is that they're clocked. And because they're clocked, they eat energy.
No, they don't have to be clocked. No, it's called combinational logic. They're actually they're registers and they're and each LUT has got and you know gates on it and a register, you know, a flip-flop.
Oh,
but you can do combinational logic, and so that it's called Ripple. So if you look at the the core 1, we have 137 LUTs. Is what the report says, because it's Ripple. In other words, it's just like your green arrays. It just the raw gates are just the answers rippling through the fabric, and then it comes out, and then you latch the answer into a register that would create a clock. But there, you know, you could have several layers of combinational logic before you have to clock it and store it, you know, for the CPU to go read it later on.
That's very good.
I'm gonna send you one of these when we get it done.
Okay. How many picojoules per instruction?
Oh no, it's not going to be green arrays. No, no way. But you know, it might be 10 or 100 times, you know, more power.
Here's another reason why we probably will see fourth in space. Unlike other industry here on Earth, in space, we have what you tend to call an installed base. You have existing software that has gotten us places. You have the knowledge, you have the technology, and you have alive engineers currently employed who have used this stuff, who for their next mission are quite likely to use it again, because there is the experience and you have an installed base.
call it space heritage, and it's like one of the #1 keywords when you're designing a system. Oh, did you fly yet? How many missions have you flown? Do you have space heritage? Yep. So the biggest problem will be getting it up there and getting, you know, convincing some people to do it. And so there's a hierarchy in space. Okay, there's a huge number of commercial entities getting into the space business, and it's when I got on LinkedIn and I was looking for work, I've hooked up to at least over 1,000 people in the space business. All these different, there's a ton of small companies, and it's these small companies that we get forth into, and then they will create the heritage, and then later on the bigger companies will get on board after it's been proven. So hopefully my SBIR work, because what we're doing is we're taking a survey amongst all these people in the commercial space business, saying, what do you want in space avionics? And then we're going to write a report for NASA, and we're going to give them, 63% want 32-bit, computers, 23% want multi-core, all this kind of, these are the kind of questions we're asking them. And then NASA is going to make that, publish the report for free out there. And then all these companies can read the report. And then the idea on this startup is to actually build the hardware in phase 2. And so if we get the phase 2 funding, which we'll probably know, I think we submitted in February, so we have to, and maybe they announce it in June of next year. I'll be designing the hardware. Guess what I'm going to be promoting?
Oh, good luck.
I'm 69 tomorrow, so I don't care. The effort is it's not about making money when you get to be this age. It's about what you leave behind, right? The impact you made on society. So that's my new mindset. And even if I'm not successful, I'm gonna do it. And to me, it'll be fun arguing with these other computer science types. Oh, you gotta have, a 4 gigahertz processor, 64-bit. No, you don't. Here's a board. Go take it home. It'll be fun. It's my retirement project.
May I slip in a dreamer's question?
I've been accused of a lot of things, and that's #1.
All of you guys talked about how to improve the existing world. But as a dreamer, I always think that there could be a revolution that will completely change the world of computing. And I have a question for Chuck. Yes, I dared use your name, Chuck. Do you see a technology that will be a complete revolution of the computer field?
No, for a couple reasons. One, the current revolution is AI, which is weird because it's basically saying, pick a random complex system and it'll work fine. I would much prefer a simple system. I would much prefer solutions that have a rationale behind them. And every now and then I think, all right, we've got a fourth computer. What else might there be? And back in the early days of fourth, I expected that there would be another language coming out, which was even better. And that never happened. All the there has been no significant change in languages since Fortran. And that's what, 50, 60, 70 years ago. That's appalling. Has no one got any imagination?
I beg to differ. APL, which actually predates Ken Iverson's point was to be able to express algorithms as succinctly but executably, and so it evolved from array algebra. So you can write down the mathematics as succinctly as any textbook or anything like that. And now it's in open forth. That's the point of what I've spent these years on, is to go and make this bridge from the simplicity and the expression of the problem to the simplicity on the fourth end and interfacing with the sequential machine, the silicon, going from arrays or conceptual arrays to the arrays in the silicon and all the gates and the switching of the gates. And that's where, what was it? It was 40 years ago or whatever when I saw the Byte magazine on fourth, and it was like, oh my God, this is how you create a dictionary. And then you're off to the races. And what's the vocabulary you should make? Well, I mean, I was already in APL, and so obviously the thing was to make the path from the, map APL into fourth, and because, man, I mean, so having and the real barrier is actually a dynamic allocation of dynamic creation and destruction of lists.
You're right. There are three languages, APL, Lisp, and Forth, that break the paradigm.
And what I call the algol languages, which is essentially everything else.
Right. And which dominate today.
Yeah, but you know what?
The other thing that complex languages have caused are complex protocols. The protocols for USB, for internet, IP are much more elaborate than they need to be. And they're all 50 years old. And no one is trying to simplify the protocols.
Well, actually, I was very impressed when HTML came along, and it was opening token and closing token. And actually the closing tokens were just the opening tokens with the slash in front. The simplicity in that structure struck me as having required years to achieve. And actually XML, which is sort of a purification of it, and I guess there are these others, JSON, I don't know, but I mean, the thing is to be able to just turn any of them into lists of lists.
That's true, except that would be much simpler if it were in reverse Polish, postfix notation. Would vastly simplify.
Absolutely. Reverse Polish. This is one of those brilliances, and this is why I say APL. They go even further into Byzantine. They found semantics and syntax in a way that you have to really know what the hell the computer's thinking to be able to parse the damn sentence. Reverse Polish, absolutely. I mean, that's the order of the world. It's
well, amazing, good idea, Bob. And we are in a fourth group and in a fourth meeting, so we will keep talking about fourth
conversation. because this is the thing, is it's the future of language. And fourth is, without question, is the virtual machine, as Don said. I mean, it is that thing that gets you to the point where you have a dictionary capable of extending itself.
So Chuck, I have an answer for you on the future language. English. Star Trek, the Star Trek computer. And there's no better language to build English communications with a computer than Forth. End of story.
It's the only one that truly allows you, because you're defining words in the sentence that they're in, and you can look forward in the sentence, you can do whatever you want. I mean,
Don and Bob, we continue and we chat about this on the fourth cafe later after the meeting, but let Cornelius read. We have 7 or 8 messages from friends who are not talking, and we want them to give the chance to say something to Chuck.
It's fantastic to be able to talk directly with you, Chuck. It's just as wow, you know.
Okay, Pablo had a question. Quote, about floating point numbers. One of the things I learned from Forth is that it is possible and desirable not to use floating point, but currently there is a lot of hard dedication to this. It seems like a contradiction. I don't want to add support for floating point in Forth, but I need to call functions where this type of parameters are required. Is there any advice that can help me deal with this problem? To make matters worse, transforming in numbers from fixed to floating point requires 1 division. So it comes down to, how do I format and pass floating point parameters to functions? How do I deal with the result?
Well, you write your own functions. It is not hard to do. And when people say functions, they usually mean sine and cosine and exponential. Those are singularly easy to do in, say, 32-bit precision. Floating point was a crutch that led to immensely complex hardware and immensely inaccurate software 50 years ago. It needs to be rethought. Modern systems of units don't have large dynamic ranges. You're talking about light years. You're talking about nanometers. You're talking about units of 1. The various application areas do not need floating point and are not facilitated by floating point. Floating point is a scam, just like complex protocols are a scam. They're supported by engineers with a embedded interest, not by any rational justification. Write your own functions. Square root is trivial. Sine, cosine are easy. Arctangent, a little bit harder, but not bad. And what other functions do you need?
I mean, I personally cheated my way out of that. Take a 32-bit integer and treat that as 16-bit decimals and the rest of it 16-bit fractions. works like a charm. Your regular operations tick as ever. The higher 16-bit is your integer part. The remaining bit is fractional. Works like a charm, is fast. You don't need a floating point processor and all the awkward interfacing, and you don't need separate libraries to deal with a different number format. You could basically reduce with reasonable precision your floating point problem into a fixed point, into a fixed point problem. It's just you don't have 32-bit integers, you have 16-bit and a 16-bit rational part, and we all go back to sleep. If that's not enough, you could blow this up to 64 bits. But quite frankly, those few graphics libraries where I had the need for any kind of fraction was happy enough with 32s, and that was it.
Often called Q16, I think.
Yeah, does the trick. I mean, let's face it, I want to draw a line on the screen. From here to there, I have reasonable graphics resolution, like 1900 by 1000. I can kill that with sufficient precision with 16-bit decimals and 16-bit fractions. And so far, I've not seen any reason to really go floating point for something that I can kill fixed point.
Absolutely.
In an FPGA, you could make it 36 bits wide.
Yeah.
43. So you could actually fine tune. If you need a little more precision, you just make the data, you just define the data bus width, which is just a single line parameter in core 1, and then it's, you know, your data bus will be 43 bits wide, whatever. And if you need more precision.
And these days, we have the scalability in hardware, and quite frankly, most software problems don't need that much. Okay, if you are in space and you need to hit something with reasonable precision, a couple extra bits might not hurt. But down here,
scaled arithmetic is the way to go, I think. I never use floating point.
Now, when you consider a space trajectory from Earth to Mars, which is what, 50 million miles, and you need accuracy to within a meter, then you need rather large integers or double precision or something. But you certainly don't need or want floating point. That would be insane. And yet that's probably what they're using.
ARM itself has said that the floating point unit, just the floating point unit, is larger than the entire integer CPU itself on a Cortex-M microcontroller.
Sounds about right.
So you have that many more transistors to worry about in the high radiation environment.
The smaller it is up there, the higher the chances that it will get fried.
And the longer it's up there. Because what's interesting about space is the silicon degrades over time. Isn't that interesting?
Yep.
So does software.
Yeah. Except for Voyagers, they're robust. Deidre.
Yes, they are. Yes, they are.
Hey guys, may I ask my question? It is also on the list in Facebook.
Go ahead.
Yeah.
Please do.
So may I share up my screen just for simplicity?
Please. Go ahead.
All right. Just a moment. Can you see it now?
Yes.
So, Chuck, my question is more about probably your early versions of Forth, when it probably didn't have any dictionary yet. Let me explain. I started experimenting with Dr. Ting's eForth, namely its implementation for Intel 8080 processor. I guess you still remember that chip. And I tried to understand how it works from inside. And what I did, I created the inner interpreter, next step. This is the pure assembly code. Then couple of other primitives, do list, which runs colon words, do lit, which puts numbers on the stack. And then, so this is the only assembly, only code written in assembler in 8080 assembly language. Then I created, three definitions, like which just print some 1, 2, 3 symbols, letters, and after that, my program looks like this. You can see it's kind of proto Forth. It's not assembly anymore. It's kind of medium level language. It's amazing. It works. So my question is, did you use the same approach in your very early implementations of Forth? Is it something you did historically?
The very early versions of Forth were like that, with very little machine code. But I gradually evolved to the point where I added more and more machine code in order to get performance, because nobody was interested in a slow language. You had to be able to match assembler speed in order to be acceptable. And one of the surprises I had with not early, but medium time Forth was that Forth was smaller than assembler and faster than assembler. And that was most satisfying.
Yes, this is something I noticed also. The program becomes just a number of bytes which run like a real program, and yeah, code is very compact. And also, Chuck, do you think this approach is still good for very tiny devices like microcontrollers, which have, say, 64 bytes of memory and just 1 kilobyte for program memory, like 8013, for example? My device with that processor, Intel 8080, has only 2 kilobytes of memory, and the smallest implementation of Forth is I've known is more than 4 kilobytes, so it doesn't fit into that memory. Do you think this approach is still good these days and for very small devices?
Yes, with a small device, you might have to cross compile your code onto it if it's not big enough to hold Forth itself. But that's still a viable way.
Okay, thanks.
Good. What's next?
Speaking of English as a language for communicating with computers, I don't do that. When I'm doing a Google search, I could type a sentence, question, but I don't. I type keywords because it's much quicker and more explicit. and less subject to interpretation. So I don't see English as being a language suitable for computers. Fourth is much better, but jargon is just as good.
Yeah, who feels like typing COBOL length statements to get something done? Admittedly, COBOL is very powerful, but hours later, and it's only one statement. Okay, next question. Alexandre Dumont. I hope I didn't completely butcher that name. Is he on here?
No, he's not in a meeting.
Okay, then I'll ask for him. Regarding the different threading models, in parentheses, direct thread code, indirect threaded code, subroutine thread code, token thread code, and so on. What was the first threading model? How did the other models appear? Did they appear, quote, naturally, unquote, driven by the different target processor and instruction set architecture or other considerations?
The first through fourth were indirect threaded code. All of my fourths were indirect threaded code until I transitioned to subroutine threaded code. Direct threaded code was someone else's. And it didn't depend on the hardware as much as the mindset of the programmer. All of these techniques are comparable to first degree. The second degree, the only choice is subroutine threaded.
No, that actually makes, yeah, I like that. Because I was fixed to embark on a directly threaded approach too, but subroutine would save me some headaches. Huh. I need to mull this over.
Now,
Okay,
Chuck,
thank you.
in your green arrays chip, isn't that token threaded? Isn't that token based? I shouldn't say token threaded, but it's a token based scheme in your green arrays chip, wouldn't it?
I'm sorry, I didn't get the question.
So I'm thinking in terms of an FPGA or an ASIC. So in the core one, for example, you know, each opcode is basically a token, right? It's an enum. And so in green arrays, didn't you do it that way, or did you have another way that you implemented the chip?
Well, green arrays has a subroutine call instruction. So it's subroutine threaded. The subroutine calls are mixed with tokens that represent simple instructions. But really the whole point of fourth is that you reuse code, which means call subroutines.
Got it. Okay.
Yeah, there's your installed code base in subroutines, nicely packaged. You know what goes in, you know what pops out. It's tested, you've used it before, don't touch it, never touch a running system. It's your building block. You build upon it, hint, installed base, and it's proven to work. It has how many space hours on its back? That. Perfect. What else do we have? Oh, here's a loaded one. Arduino STEM education. My question to Chuck, Which is the most difficult microprocessor to run forth and why?
I don't know much about current microprocessors. I think the most challenging one I ever encountered was the 1802, which was 4 bits or 8 bits, very sparse instruction set. Forth worked very nicely on it, but it took some real twisting to make it fit.
So it would be an early CPU, not a late one.
Yeah, one of the very first.
Yeah. Yeah, they had some interesting quirks. I think I remember one which didn't have an explicit subroutine, jump to subroutine call. You basically had to go to a memory address and do your own stack management. I have to find out which one that was. For Forth, that would be an interesting nightmare to have.
Didn't the 1802 have the ability to have like multiple stack pointers?
I think it had 16 programs. I had a Cosmac Elf, which is 1802, and it has some unusual attributes, and plus it's a first CMOS processor, as I recall. It had like 16 instruction pointers, or 16 to something. It was unusual architecture.
The PDP-8 did not have a subroutine call. You had to, yeah, you had like one, yeah, didn't, bottom line. I think Ken Bow could probably say more about it.
I think the Zilog Z8000 had you could specify which register your stack pointer was. There was a convention that you always used the last one, but you didn't have to. Better not mix that up.
We have Philip Eaton in the meeting, and he's so quiet. He has no questions for Chuck.
Actually, no, I do have a question for Chuck. Well, not just for Chuck, for anyone who's interested, really. One of the things I've been thinking about over the past couple of years with Forth is that you tend to, Forth is a very flexible compiler. That's the way I see it. I'm working mainly at the moment with 8-bit systems, but I think it's the same for 16-bit systems. What we don't tend to get, apart from in commercial Forths, are options for optimizing what the compiler gives out. It seems to me that if you compare a program written in C with a program that's written in Forth, the C one will be faster. And the reason I see for that is that the Forth version has a very primitive and unoptimized compilation. Now, I don't think it needs to be like that because it's a very simple compiler. You can put in as many optimizations as you want, but people tend to not bother. And I'm wondering why that is the case. And in my own case, compiling for 8-bit platforms, which is what I'm doing, which is basically writing some games, Forth is relatively slow. Obviously, it's slower than assembly language because that's hard-coded directly. And it generally is slower than C, of which there are some optimized C compilers that seem to do a reasonably good job. But Forth doesn't have that level of optimization. It seems that no one has bothered to do it apart from the commercial vendors, and possibly there are some native code generating Forths that do have that, but obviously no one's going to go back and rewrite any 8-bit compilers to do that. My question really is to do with why were there not really many optimizations built into compilers back in the early days for 8-bit machines? Is it that they just weren't around for long enough and everyone shifted onto 16 bits and then it was less of a problem? And that's sort of answering my own question, but I'm just interested in people's thoughts on it.
There were Forths that made a point of optimizing things. Really, the only range for optimizing are the stack operations. If you're going to want to do a swap drop, you can replace that with some optimized machine instructions. But it added a lot of complexity for a very small game, especially when we moved to subroutine threaded code, where we would mix machine language and subroutine calls. So the machine language could be used to optimize the stack, and you didn't need the automatic optimization any longer.
Was that where the target was able to be used as a fourth computer? Because certainly in my commercial activities in the 90s with Forth, everything was cross-compiled. And whilst we did use an interactive prompt on the target when we were out in the field trying to debug a system, that was really useful. Most of the dictionary that was compiled in would never be used interactively. So I then think about that a bit more, and I think, is it actually necessary to have an actual fourth computer running on the target if it's an embedded system? And that makes me, if you didn't need that requirement, you could then make it a native code system where what got compiled to the target was something that you couldn't run interactively anyway, but you'd have the benefit of being able to write it on a host PC with all the benefit of being able to use Forth, and then the compiler would compile something that's actually runs really fast on the target because you don't need the interactivity. Did that ever happen?
Do you have code words in your Forth?
Yeah.
Write the slow stuff in code words.
Oh yeah, I'm not saying I can't do it. I'm just saying I wonder why it was never done in the past. I mean, for me now, if I'm looking at optimization, what I'll be looking to do, because memory these days is free, even on an 8-bit system, you can have as much as you want pretty much. Nowadays, what I actually want is a slider, and that slider says fully interactive Forth, and at the other end of it, it says completely non-interactive Forth, inline everything, make it super quick like a C compiler would. And there isn't a slider on anyone's compiler yet that does that.
32 micros cost $1 today.
Maybe they do, but a Vectrex console, which is sitting on my desk, is owned by people right now. Yeah, but there's my target.
What you could do,
oh, well.
What you could do is put some of the slow subroutines like your block move, your block compare, and your block search into a code subroutine. And like, I think I did that with some of my early Forths that were 8-bit, and that would really improve performance on a lot of things. Because a lot of, if you do it in Forth with all the overhead with looping instructions is a lot. And you can, if you do that in assembly language, you just make a subroutine for it that really helps a lot. But then you have you're making your higher level code words instead of colon routines, you're making them code subroutines, like what Don said.
Oh yeah, I have no problems in actually speeding the thing up. It's just that I have to do it manually, and I'm surprised that there are not many Forths out there that have any optimization built in.
No, wait, this is, I think we're getting into the apples to oranges terrain here. If we look at compilers have one first and foremost task. They take high-level language, which can be fairly close to what a system does, like in C, or it can be way removed, like as in Java, where you have a virtual machine in between to make things work. They take very complex, human understandable, hopefully, see my rant on void star earlier, they take very complex statements and dumb them down into machine instructions. That's something that the parser does. In between, you have an optimizer, which might or might not work hand in hand with a code generator to target specific details and capabilities of the underlying CPU. So you take something that is very, very complex, phrased in a very complex manner, and dumb it down to a machine that understands very simple things and does these very simple things very fast with the resources it has. The amount of resources has gone up over the years, and so have the complications of the instructions underneath that have been optimized for deep pipeline, multi-threaded, threaded executions, where the CPU's microcode does a lot of the heavy lifting. In Forth, we don't exactly think this way. We have a mechanism that lines up execution of code words one after the other. So we tend to, because the language provides us the means, optimize stuff as we write. And once we have a block that has been written, we tend to reuse this as a subroutine, aka as a word. Subroutine equals function equals procedure. We have formal parameters that we pass on the stack. Practically everybody does that these days. C, Java doesn't really matter. We shove parameters on the stack, execute a word, reap the results, carry on. In this case, what we can optimize is getting in and out of a subroutine, make that snappy, we save time, and stack operations. So, in other words, a lot of this compiler shoehorn into given architecture optimization doesn't quite apply because we're already underneath all that. Close to the wire, the mindset is different. So from that perspective, yes,
I disagree.
To get some time out of the mix, it would make sense to say we have a space and performance constraint on the target hardware. By all means, let's compile that thing and drop all kind of interpreter environment, because the target will never ever offer or will have to offer interpretive ability to some user, because end user will not see it. Compile the thing. Compile the whole thing, maintain the stack-oriented nature of the machine. Just let's get all the search and thread overhead out of the way and go direct. At which point in time you might lose the ability of ever debug something in the field, but then to debug something, you need the exact scenario where that triggers a bug, that displays a bug, that makes the bug reproducible so that you have something at the end of the day that you can test against, which you can then slink into an interactive environment and see things blow up. But as far as compilers go, Forth offers me a way to hand optimize the living daylights out of something, instead of hoping that the built-in optimizer does the right thing and not introduce some really interesting errors that then I have to track down, fiddling with a plethora of unused or ill-documented compiler flags that may or may not tell the optimizer what not to do.
I
disagree with you.
But I don't think
agree.
any of this answers the question that Philip had, right? I mean, the reason why in the 80s, right, nobody worried about optimizing Forth was exactly the same reason that people weren't using C compilers on 8-bit targets in the early 80s, right? Which was, there were, for any time critical code, everybody was writing directly in assembler, right? That was what happened for 30,000 games on things like Sinclair Spectrum on the Atari 2600. They were all mostly coded directly in assembler because that's the only way you can get them to run fast enough. Now, there were a few companies that use Forth, like people use Python, as a high-level prototyping language and to run the high-level code, right? And then they'd optimize specific functions into assembler when they needed the speed. There wasn't really the trade-off of writing an optimizing compiler in the early 80s just didn't make sense, right? Now, if you program on things like a Sinclair Spectrum or a Commodore 64 today, the people programming, you can get C compilers, a small C compiler. And there's also Forth. I mean, we've got one of the guys on the call that writes Forth for Sinclair Spectrums, right? So in the 80s, the situation was everybody had to know assembly in order to get fast things running like games and flight simulators and all this sort of stuff, right? In my opinion, the situation is different today, right? On PCs, generally everything's fast enough, right? People write for Python. Python's known for having a very, very slow interpreter, right? But generally it's fast enough. And when they've got something that they've got a particular problem, they use a compiled C library or an assembler library. It doesn't really matter, or compiled Lisp or whatever it might be, right? To speed up particular operations, right? That happens today. And you can use Forth exactly like that, right? You can write all your Forth. If you've got a problem, you don't even need to drop in assembly. You just call on a PC, you call a compiled library. Now, on the microcontroller world, as Peter knows, there is things like MECrisp. MECrisp is a native code generator for ARMS, and it's done a version for RISC-V. It's got a version that the standard Forth compiler is 16K. It's got a version that's 20K that does register coloring, register optimization, right? It's pretty good. On the commercial side, there's people like MPE, right? That's a native compiler as well. But for most people's problems, they don't actually need that level of speed, right? If you have a look at Arduino, the libraries to set a bit.
They did 30 years ago.
So well,
I needed it 30 years ago.
What was that? Sorry, say that again.
You say that people don't need that speed. 30 years ago, I didn't need that speed.
In the 90s, people were starting to switch to C, right? Wasn't everybody, but people were starting to switch to C in a big way on the fast stuff. But it was still, a lot of the games were still being coded in 68,000 assembler.
Oh, hang on. We had an Atari guy come into the group and answer some of these questions already on the.
Yeah.
So I think if I remember what he said is they used Forth to make the games, but they didn't use Forth in the games. And the reason was Forth was too slow.
And that's exactly what I'm doing today.
Yeah, and then what he did is they said they went to C, and this was before, this was like in the mid 80s, they switched to C. And they
People switched to C when the 16-bit processors came out, and then 8-bits weren't really relevant and Forth wasn't needed because the speed that you got by moving to a 16-bit processor meant that the games were better enough than the 8-bit games that they were sellable without really having to squeeze the performance out of the processor at that point. So I think that's why they moved to C on 16-bit processors, because they got
Philip and Rob. We have in the group, but regrettably not today in this meeting, William Falk, who lives in California, and he was a professional game developer. He sold the games at the Comdex in Las Vegas, where he worked for very large game companies and made in Forth.
Yeah.
In the 80s.
Yeah, Atari made some games in Forth that were.
So, but there's nothing to stop us writing and optimizing Forth compiler, right? It's not an unsurmountable problem. It's just the target, in my opinion, the target niche has always been small enough that apart from specific things like MECrisp and MPE Forth, that it's always been, most of the time people want something that's rapid to prototype, and then they just optimize the bits that they need to. And maybe you've got a special case, Philip, but it is, having still writing occasionally on 8-bit machines, it is an interesting problem 8-bit machines are, because they're so much slower than modern machines.
Philip, are you using, do you understand Create Does?
I'm sorry, say again. Create Does? Yeah,
Create Does.
That. Yeah.
So if you use Create Does and you develop your own compiler words, then you can create structures and stuff that would take more code in C than in Forth. You can compact more stuff in a game in a limited memory space in Forth than you can with
No,
C.
I get that. No, I get that. I don't have a limited memory space. Memory on an 8-bit is you know, there's as much memory as you need these days. I mean, I do it for a hobby, and it's a
Okay.
The environment is one that has a number of limitations, but memory isn't one of them. And as I say, the optimization to make something run as fast as a C game, for example, I have to do all that optimization myself. And it's just what my question or statement was that I was surprised that there were not more optimizations added into Forth compilers or Forth assemblers, depending on how you want to look at it, back in the 80s and 90s when it would have made sense to do it. I know in the 90s, my company were using MPE compilers. We had a few limited optimizations in there, but not ones that would say, okay, you've got a program that compiles down with classic Forth to, I don't know, 20K, but you've actually got 64K. Now, would you like to use up that whole 64K? And what we'll do is we'll unroll a number of your function calls, so to speak, so that instead of making a call to a subroutine, we'll just put another copy of the routine in and use up your 64K and make the most processor performance that we can out of it by unrolling everything. But those options didn't exist.
In order to do that, you'd have to use like a Forth meta compiler or cross compiler.
That's what I was using. That's what I was using. Yeah, I mean, I don't. Yeah. I'm not looking at Forth many years ago, where a Forth computer that stood alone, it had access to a disk drive. It might have had a teletype on it or a keyboard if you were lucky, and a monitor. But honestly, from the mid 80s onwards, you didn't need any of that. You could cross compile everything to a target. So all this idea of having a Forth computer running Forth and people using it as a Forth computer, I've never been involved in any of that. Everything I've done professionally was embedded systems. So as far as I'm concerned, what I wanted was a compiler that would produce something that was what I needed on the target. And interactivity was nice and useful for when I was bringing up new hardware. But once I brought up that new hardware, I didn't need it anymore. I needed something that worked on a PC that would compile down to a target. And that's where all the optimizations could be really useful. And as I say, there were some professional ones in the MPE product, but that's sort of all the ones I've seen, really, to be honest. Yeah, I'm just surprised. That's really my statement there. I can make all these things faster if I want, but I'm doing it for me only. I'm surprised that no one made compilers back in the day that did it for everyone, apart from the professional ones.
Just as another note, I mean, having written a lot of C code in the 80s and 90s, a lot of the C compilers were terrible as well. I mean, we had lots of problems getting the speed out of those compilers. We were doing software modems, B22 and upwards in 16-bit processors that were run at 32 meg, and trying to get the compilers to generate any reasonable code was an exercise in futility a lot of the times. I mean, the last 20 years, the compilers have really come on leaps and bounds. But my recollection is a lot of the commercial embedded compilers in the 80s and 90s were terrible, the C compilers. I mean, we worked with IER a lot and ended up writing long reports about how they should change their code generation, right? For lots of different micros, because it was so terrible for something you paid. We were paying, $5,000 a seat for 20 developers, right? And the code generation was awful. And a lot of the micro manufacturers going, well, just use these C compilers. And we were like, but it's terrible. How can you possibly advise this?
I think this is like comparing a sports car to a backhoe. Forth, what the features that Forth has is something that C would never has and never will have. It's impossible. If you want to write code and compile to the fastest thing, C. But what do you get with that? You get operating systems that are 8 gigs. Come on. So it's apples and oranges. If you can't just compare one small feature, which is speed, because with Forth you can get a lot more functionality. I mean, a factor of 10 functionality in the same hardware space than you would with C, as an example. You get incremental compilation, you get interpreter. The compiler is inside your application. It's not sitting on a laptop somewhere. So, you know, it's kind of comparing apples and oranges. Your whole focus in life
we have a
is
hand raised.
speed.
A hand raised from Ken.
Good day, everybody. I've got 2 or 3 things to say. Firstly, I'd like to offer my best wishes from myself and everybody in this group to Chuck on his birthday that I believe was yesterday. Happy birthday, Chuck. Secondly, about 10 minutes ago, we had a question regarding what was the easiest and what was the most difficult machine to implement Forth on? Well, I'm going to regurgitate something that Brad Rodriguez wrote about 30 years ago. In his opinion, the Motorola 6809 was the best target, best 8-bit target for an 8-bit Forth, and the Intel 8051 was one of the worst. I've made some inquiries about running Forth on a PDP-8, and I only know of about 2 people that have addressed this, and both of them say that it was particularly difficult because of lack of an efficient subroutine mechanism. I would go on to say that any target for Forth, it needs to be able to implement 2 stacks and be able to implement them efficiently, and also be able to implement efficient subroutine mechanism. So if your processor can't do that, you're not going to have an efficient Forth. I have spent some time looking at Forth for classic 1970s microprocessors, and I've looked mainly at the Z80, and it takes 10 cycles to pop and 11 to push, or possibly around the other way. And unless you can do efficient stack manipulation, you're not going to have a good processor for Forth. And hopefully later this year, I'll be bringing some of my recent explorations on early 8-bit processors to light. I've just seen that Brad has said that 6809 and MSP 430 are great targets. I tend to agree with them. Anyway, that's it. Happy birthday, Chuck. All the best.
Cool. Next question, please. I have another one from Facebook. Will Blake is asking, did CPU designs for languages like Smalltalk, Algol, Lisp, Ada, and Prolog motivate the Novix and SH Boom, how do you pronounce that, designs for Forth? And was Chuck aware of the Forth chip designs emerging from Johns Hopkins Applied Physics Laboratory?
Isn't that a shaboom from a song? Sorry.
Yes. I knew about Johns Hopkins. I think they were the first Forth computer. but I didn't know much about designing computers when I did the NC 4000. And that led me to a micro-coded instruction, which was very efficient, but more elaborate than my current tastes. This had instructions with a lot of bits, and the bits all had meanings, and it led to a very efficient implementation and a relatively simple compiler. But I moved away from that. The other languages didn't really factor in. I was focused on Forth and trying to optimize Forth hardware.
Why go away from the bits have meaning approach of the Novics? I mean, okay, fine. You would have to redo hardware. No, you wouldn't, because Forth does not have that many elementary operations. Once you've covered them all, you're done. The rest is software.
Yep.
I'm thinking loud again, am I?
The bits were used to select an ALU operation.
Yes,
To select
they were.
a shift after the operation. I think they said something about a conditional.
Yeah, I saw that. There are bits in the Novics opcode that select that. That's the moment when I wish I would have a screen big enough to look at the assembly language manual of the Novics and RTXs, but not on this laptop.
I have to take a look at the Novics instruction set.
Oh, it's a beauty. That's one of the slickest things that I've ever seen. And zero microcode, it's all direct. Love it.
Because you can add that stuff to the Core 1 easily.
Uh-huh. Yeah, it's just gates. There's no microcode, nothing. Everything executes in time of one. Well, a long literal fetch does not. And a long literal store does not. Because you have the you have the opcode, which then causes you to the next cycle to fetch the memory operand, but everything else, fast as can be, doesn't get any better. That's how you could allow yourself to bit bang a serial port while doing things. And I only got to the point that I overran that when I tried to drive that thing from the outside using a little bit more modern, a little bit more faster machine than back in the day. When you actually have to slow down your host because otherwise you overrun your target.
Yeah, one of the things we were doing in the Core 1 is you create an opcode just using enums. And then and you can create any opcode you want, and so it's basically the opcodes of the processor are tokens, but then when you start compiling into memory, it's CFA. So you can very easily, with a few lines of Verilog code, which everyone knows C here, is C syntax. You can add your own custom instruction to the processor. If you want to bit bang ports and stuff like that, just absolutely trivial. Or if you want to bit bang a port, but have some processing in between it, like maybe you want to strip bits out, or bitmask stuff, or do some additions and subtractions. You can embed that all in your opcode for like a customized application where you got some sort of IO where you want to do something more than just so that way you can optimize your processing. That you look at your 10 usually with micros, 10% of your code takes 90% of your time, right? So
yeah,
you,
no
you
kidding.
take you take the 10% and you make them opcodes. In this case, in the core one, and you write them in system Verilog, and now they're running at the speed of silicon. You can't get any faster than that.
Right. Nice. More questions?
I'll risk
Yeah, I have one. Hi, Chuck. I was wondering if you could describe a little bit more about your experience in making the jump from software forth to hardware forth, and what did you have to do, and what was that like?
The NC4000 was the jump, and it was all Forth software that designed that chip. I wrote simulators, I wrote compilers, I used software to optimize the design. It was very, very software intensive. The hardware itself was designed by another person, Bob Murphy. And I was kept busy keeping up with him and trying not to sabotage this hardware he'd already developed in the course of my simulations. The chip was very, very thoroughly simulated. When it came out, it had 2 bugs. One had to do with the multiply and was inexcusable. And the other had to do with interrupts, which I couldn't simulate. I had no way of creating a random event and running it through the simulator. And those were corrected in later version. I had never had anything to do with hardware before. And it was quite a challenge to learn about gates and bits and bytes. In retrospect, I think I was pretty lucky it worked as well as it did. But it had to do with the simulation.
Can you elaborate on when you decided to design your own chip? Designing like that blew me away when you did that.
And that in the 80s.
What were your thought processes? How did it go? What kind of challenges along the way? Tell us a little history on how you designed using you invented color forth first, right? And then you went into designing the chip coding.
Well, this was 2000. This was 20 years later than the NC4000. But I can't remember my motivation. I know I was working with Dr. Ting, and he was financing the hardware. And this was after Shaboom. So I had had an experience with small small instructions, small bit instructions. I guess I just figured that I could do better than Shaboom. Shaboom had 8-bit instructions, and they were more bits than I needed. So I figured 5-bit instructions would be nice, and would be simple and easy to implement. And that is true. So what I had at around 2000 was a very small processor that was implemented on a very large chip. The processor only used about 1/4 of the silicon available, and the rest of the silicon was empty. And it occurred to me that I could fill that. Of course, I could have filled it with memory, but I didn't know how to design memory. And it occurred to me I could fill it with processors. And so I did. I think I had 10 or 20 processors and about the same silicon as I had one. And then we, at Green Array, scaled it up to 144. And the real innovation, the real design was the original computer or core, which I could replicate. And indeed, it was simply a question of replicating it once the design was optimized. And the key aspect of the design was that it did not need a clock. As you say, it was a combination logic. And that was scary because, of course, you needed a clock. Everybody had a clock. And I had to argue with my collaborator about that. In fact, the very first chip had a clock pin, which was not necessary, but just in case everything else failed, you could put a clock in it and run at half speed, which I never did.
I took an FPGA class in the 90s, and it was really funny because in FPGA land, you must have a clock. You have to have a clock. You have to have clock in all your always statements. And I said, why? I'm learning VHDL. I'm going, why do you have to have a clock? I mean, because, you know, I'm thinking 7400 gates, right? And registers, right? You know, flip-flops. So we had a homework in it, and we literally made a clock, right? You know, minutes, hours, and all that. And I wrote the whole thing, and I only used one clock for seconds, and the rest of it was common. I didn't use any more clocks, and I got an A on it, but there he goes, you're not supposed to do it that way. It worked. What?
Our clockless design has race conditions, and you've got to simulate very carefully, analog simulate rise times and fall times and delays in order to make it work. And conventional simulators can't do that. So the key to designing the clockless computer was writing a simulator that could handle it.
So a couple points on that. In System Verilog and VHDL, you have what's called blocking and non-blocking statements. So blocking statements creates combination logic, and we'll do it sequentially, but it will do it sequentially in less than a clock. It goes at the speed of the fabric. Now, the key thing is, what if you have a system clock? Let's just say it's 10 nanoseconds, right? And it takes 15 nanoseconds for this opcode, say, to run. Well, so in the core one, what we do is we have a busy flag. And so when you start the opcode, you set the busy flag, and so it can spill over the opcode could be longer than the actual clock rate of the processor, and it just stalls the processor until it completes. Or you have to use semaphores, right? To say my output, you register if with combinational logic design, you register the output, and then and you set a flag that the data is now valid. So the next thing the next process that is relying on that data says, oh, it's valid data, and I can go ahead and run. So instead of in your always statement putting the clock all the time, you could just in the always statement just put is the bit set, right? And they don't teach this in school.
No. And the FPGA fabric is much slower than custom silicon because it has to handle the worst case. And it is probably impressive that they come up with cells that can handle the worst case and still be reasonably efficient.
Yeah, usually it runs about 200 megahertz is what most FPGAs run. But because they're parallel machines, you could do your, how you had 5-bit instructions, you have 32-bit wide, and then you could have 3 instructions running at the same time. So that's that parallelism. You can take advantage of that in an FPGA port.
Quite right.
May I slip in the question?
Sure.
If Fort had to be recreated today and you did it, would it be really different?
Say again?
If you had to recreate Fort today with the technology that we have, would it be really different?
No. I've tried to brainstorm a different language, a better language than Forth, and failed completely. As far as I'm concerned, Forth is it. Forth is the computer language, and everyone should be using it. And it is a social tragedy that they aren't. As far as hardware goes, I think the same thing. Green Arrays has a chip. I have tried to come up with a better chip than Green Arrays, and I can't. That doesn't mean no one else can, but I've run out of creativity, I guess. But I'm completely satisfied with the way things are.
Why did you choose 8-bit wide for the processors in the Green Array? It's 8 bits wide, right? I'm sorry, 18 bits.
18 bits.
18.
That's because at the time there were 18-bit memories available, 16 bits plus 2 error correction bits, and tried to take advantage of that memory. Now that memory went away, and in fact we had to use 24-bit memories or 32-bit memories, but the extra bits didn't cost anything, so we just ignored them.
So you wouldn't even shift to 32-bit or 64-bit today?
If you have too many bits, and if they change state, you're wasting energy. 18 bits, all those bits are used all the time, so there's no wasted transitions. To me, a 64-bit computer is ludicrous because no one uses it. The only thing you use 64 bits for is floating point, which is useless. You might want more than 32 bits for memory addresses, but that just means 34 bits or 36 bits, doesn't mean 64. But I've learned to accept the fact that the world is inefficient. The world is going to do what it's going to do. Engineers take great satisfaction in making things complicated. They've screwed up the compilers. They've screwed up the computer architectures. They've screwed up the protocols, always making them more complicated and less usable for ordinary people. You've got to be a guru in order to get into them, which is part of their motivation.
So if you were designing
doctors in medicine, they do the same. They try to make you dependent of drugs and lot of complication that many times is not necessary.
That's right. It's a sort of a principle, the complexity, that evolution will yield more complexity and never simplicity. I think that's true of Darwinian evolution, not deliberately, but just sort of inevitably.
with the low cost of silicon today, would you prefer 16-bit or 32-bit computer? I know you obviously 18-bit is your, but let's just say that if you're designing a computer today with a cheap silicon, 16 versus 32, what would give you the most powerful fourth system?
16 is too small. 18 is barely enough. 32 would be my next choice.
Okay.
I saw James Norris has a question.
Well, I had like two things. One was we learned about the combinational logic circuit. If you wanted to, check the delay of the circuit, make sure it was ready, you'd have a 1-bit path that would match the delay. We learned that in college. Just saying, my college taught that. The other is for a better programming language than Forth. What about a cross-platform Forth assembler that did the LLVM? So you could, like, for each processor, make it at least do the LLVM instructions. And if it was a Forth assembler, you had a stack, you'd get Forth. But would that be like a way to go?
LDN?
Oh, that's the low-level virtual machine that all the modern compilers compile to. So like C++, Visual Basic.
Yeah. I think that's silly. Forth compiles directly to machine code. No reason not to.
Well, the reason would be for things like branching. A lot of microcontrollers and processors have the result already in the flags register. And what Forth does is it pushes the number to the data stack and then checks to see if that number is 0. And that's pretty inefficient. That's the main reason, just to get that. If Forth had a branch instruction that didn't use the data stack, that would probably solve the problem. But that's mainly it.
In my current Forth, the branch instructions are the hardware instructions, and they use state bits instead of something on the stack. But the whole problem is with branch instructions, and you don't want branch instructions. You want your code just to be a single stream. And that's of course impossible, but very, very few branch instructions. You can actually sometimes substitute logic, ands and ors, instead of branches. But now your first question.
Oh, that wasn't a question. I was just telling Don that our college taught the thing he said wasn't being taught in college.
Oh, okay.
Well, they taught you synchronous logic, right? You should always put the clock in the always statement in the sensitivity list?
Sort of. Well, that was a funny thing. They had a homework assignment, and the assignments that when they taught us, like, okay, you have to put into a latch first, go through the combinational logic, latch the output. And for my solution, I was like, why are you doing all that? It's a combinational logic circuit. You just let it run through. And they were all like, they're like, no, you can't do that. And then 2 years later, one of the TAs came up with the same thing. He's like, oh, look what I came up with. And they started teaching it that way. And I'm like, but I did that 2 years ago.
Well, the FPGA companies were very nervous about people, writing code that didn't work or that had anomalies, and so they basically were saying always put a clock in your sensitivity list in your always statements or your and it's because they didn't want to teach it deeper than that. I was in a room of 40 engineers for a Xilinx class, and he said this right in class. 40 young engineers sitting there going, oh, I will always put a clock in the sensitivity list after coming out of that course. I mean, he basically said, because you don't know the silicon, as we change the underlying silicon and the speed and stuff, your code may work on this generation FPGA, but the next generation it could work differently. But that's where you use semaphores, register the output.
The 1-bit path that matches the gate delay in the circuit. That's your flag.
Yeah. So, if you use that 1 bit, then it's basically your flag, and combinational logic is perfectly reliable.
One comment I want to make about this whole notion of replacing branches with logic. That's one of Ken Iverson's brilliances, was to understand the power of Boolean lists. So you essentially go through the entire object that you're going to deal with, and you just simply do logic on the whole thing, and then you extract from that Boolean vector, where the things are you have to operate on. So that does an awful lot to go and replace. You just have the fundamental loop is to get through a list. But that abstraction of logic into Boolean arrays, Wolfram, actually, there was a conversation between Iverson and Wolfram when Wolfram was an invited speaker, and they happened to be at dinner, you have to look at APL literature to appreciate just how deep some of the things that have been done with Boolean lists and so forth are. And Wolfram didn't get it. I mean, my impression was he didn't get what Ken was saying.
So with an FPGA, you might use like a decoder instead of a branching, maybe. What do you think about that?
Exactly. One of the thing is, all of the early APLs in particular had true Booleans. That's a type that needs to get added to, and that efficiency of having operations bitwise Booleans is that back in the day when space mattered, that could speed up operations enormously by simply having logical operations on Boolean arrays.
So a case statement in System Verilog, for example, would create a decoder. So you build a state machine. Yes. So I think the way I'd approach it is you build a state machine, and then it's around a case statement, and then that allows you to. I mean, one of the hassles about if-then statements, it can get really crazy, right? But if you have a state machine, then it's really easy, to jump from one place to another instead of doing all this if-then logic.
Yes, that's something also you you're just doing the logic on an entire set at a time. So, and it's sort of just thinking in terms of matrix multiplications, you can always replace an entire string of matrices with one. It's just because, you know, so there's that sort of ability in terms of thinking about the problems. And those Booleans, true Booleans, were really fast and optimized in the early APLs, and that's one of the things that made them competitive in speed. When I was at Xerox in 1980, you can look at my Vita. But that's
one question. Klaus Kohl is in the meeting. Klaus, do you have any questions for Chuck, or do you want to say to him happy birthday or something?
Of course, I want to say happy birthday, Chuck. I use NC 4000 since 35 years in the past for measurement system, and now even I try to realize it in FPGA. So thanks for all.
I see, James, do you have a raised hand, your hand?
Oh, what to go back to the other thing? What if we added a branch forth instead of just if? What if you had like if carry clear, if carry set for those processors that don't, like, you have a fourth that's built into it, but for like regular processors like the x86 that doesn't, if you had like an if carry set, if overflow instruction, that might solve some of the speed problems. You might have talked about that before too, but I don't remember the answer.
I don't think it would make a great deal of difference one way or another. That's not in the critical path.
Who else has questions? I see Alvaro is in the meeting, and Matteo Vituri from Italy. Do you have any questions? Geoff Riley from England. How are you, Geoff? Who else has not? Yes, go on.
Yeah, I'm a bit out of it at the moment. As you know, we've had an unfortunate time in the UK over the past few days, and I'm a bit preoccupied, to be honest. But I will wish Chuck a very happy birthday for yesterday.
Thank you.
And Atle from Norway. Do you have any questions for Chuck? We can't hear you. No questions. Rolf Hammerling from Germany.
Hello, Chuck. Happy birthday to USA. Is there any birthday present you got today which is worth to mention?
Not that occurs to me.
I have a question. Yes, I do have a question. Greedy old me has a question. Chuck, is any of this old simulation code for the Novex, is that still around? And would it be something that could be put online? Like the software
I have no idea if it still exists.
Yeah,
I certainly don't have a copy of it.
Yeah, the software archaeologist in me is just wondering.
If I had to, I would rewrite it if I had to, rather than try to find it. That's always been my my strategy that I've got 2 or 3 laptop computers in a closet, each with a different version of Forth on them. And I'm keeping them because I think I might someday want to go back and retrieve that software. But in fact, I don't and won't. They're garbage.
Testing your memory a little bit. How many lines of code for the simulator? Do you have a rough idea how many lines of Forth code it was?
Oh yeah, it was 20 or 30 blocks, 1K blocks.
That's amazing.
My largest application ever was the simulator for the green rice chip. And I think that was like 60, 70, 80 blocks, something like that.
Which is mostly white space.
More than that, I couldn't comprehend. And I squeezed out the white space by compacting it so it would fit onto a floppy or
right, those
two
things.
copies on a floppy. I had 300 blocks of code on a floppy, 2 or 3 different applications.
So we're talking about building some new a new computer here on FPGAs, and Klaus has been working on it and other people. Looking back at storing data on a disk, do you still think blocks is the most efficient way, or some sort of other file structure for efficiently using disk space?
No, blocks, definitely.
Okay.
I've seen other people use files. I've used files myself. The block, if you compare Forth with English, the block becomes a paragraph. And that is a very, very useful concept in organizing your language. And I think a 1K block is ideal because that's what you can display on the screen.
I see, Chuck, many young programmers complaining about blocks, but I use blocks and I am used to work with blocks and screens, and I found them fundamental for Forth understanding and also for keeping the code small. And I was very, very productive with blocks because I had in my mind beginning of, for example, block 15 is something, on 16 is something else, and on, for example, on block 20 I have the serial words for talking in eras 232, and so it was all in my mind, and so I could jump only with a key press from different, it was files inside a larger file. And this concept is the concept of Forth being an operating system. And this is something modern programmers don't understand. If you use Forth, you don't need any operating system. You can work bare metal. And 1K is RAM. When you work with hardware, you know your memory is divided in K. So you have 1K, 2K, 4. This is normal for me.
The original concept of Forth as an operating system had to do with disk access. You had to be able to retrieve things to and from disk. Now that's gone away. Now memories are so large, disk is irrelevant. I load my Forth and all my source code and all my databases in the memory at the start. And then it's always there. So
And
the world
when
has
people,
changed.
yes, sorry.
So go ahead.
When people start working with files and file names, the things got very complicated.
You have to open a file. I've never understood why. And then you have to close a file. I don't. I've got code which can read things from disk, read files from disk. I don't open and close them. I just read them or write them.
And you don't need any directory. You make a quick index and you see everything it's there. So it's fantastic.
Yes, yes. It's Forth accommodates the functions of an operating system. One of the things it classically did was multi-thread. You could have several Forth applications running at the same time. Well, personally, on my personal PC, I don't need to do that. That's gone away. I can only do one thing at a time because I'm looking at it. So again, that aspect of an operating system is a creation of people who wanted to make things complicated. If I want to run several applications at the same time, I'll have several computers. They're cheap. Why not?
Absolutely hate RTOSs. And every place I work at, first thing you say, I want to run an RTOS. No, you don't.
I have to use an operating system like Windows or Linux. And so at the moment, I use both types of file system, a normal file and even blocks. If I use a bigger system on the PC, like WinForce, and I use sequential files. Also, if I use very small microcontroller only connected with terminals, I use sequential files. But if I use a microcontroller connected to a PC, then I use block files, because then I can send one block for addition or for manipulation. And so it's the best of both.
Yeah, when I was working at Redwire, our software team, so we had this beautiful FPGA system. We had a great system Verilog coder. I didn't write the system Verilog code. Did a great job doing all this stuff. And the software guys were writing an RTOS or doing everything on an RTOS. Then, you know, sometimes the time slice wasn't quite long enough for what we're trying to do. And they had all this complicated stuff, you know. Oh my God, it was horrible. And you know, it's normal for them. This is computer science today. Yeah. This is the way you do it. Use an RTOS, use time slicing, and if your task doesn't finish before it's done, you know, you got complications you got to deal with.
Especially on microcontroller, I see more and more problems because especially the small integration compiling on Forth is very difficult because the internal flash are normally bigger and bigger flash groups. But I also see the opportunity for using new microcontroller using, for example, MRAM internal, not only MSP430, but also for the high-end processors comes more and more MRAM, which can be manipulated on bitwise. And so it will be better, but at the moment it's worse because some microcontroller has blocks of 128 kilobyte. And so it's not really changeable.
Yeah, if you look at my videos on the Triune OS, it's a way better way of multitasking, and we're going to be implementing that on the Core 1. It's basically a foreground background type model with hierarchy. I don't want to take up everybody's time, but you can see some of my videos out there on SVFig and also for 2020 videos. makes a lot more sense. Just that you let a task run until it's completed with background tasks. So if you want something to run in parallel, you just make it a background task. On the core one, you can just make it another always statement. So it's just another process in the chip. You could have hundreds of background processes running in the background of your fourth computer. Doing SBI. Maybe you have a dozen SBI things, and you write it all in system Verilog, and then you just have these buffers that your fourth goes and reads and writes, and you have flags telling, basically the buffer doesn't update until the date is valid, so you don't really need a semaphore, but the fourth just goes and reads the very latest data that's in it, and it's just a really simple model for. I think it's revolutionary, but that's me. And one last thing I want to say. So we have 100 space robots on Pluto, and you need to update the software, and you're using C, and you have to upload on this very low speed data link this huge binary blob and update 100 robots. It might take weeks. If it's fourth, you just update the code that changes, they're deferred words, you replace it in memory, and while it's executing, the new code is the next next cycle, it runs a new code. So I think what's going to happen in the space business is they're going to be forced to go to fourth at some point, because the companies that start using fourth will have much better performance, and they can use low speed data links. It won't take weeks to upload the code. So I think that's the kill. We needed a killer app, and that's the killer app right there, space, which fourth has a lot of history in already.
But the problem is at the moment, more and more application comes with wireless stacks in different flavors. And for example, the new Meta stack has a size of 1 megabyte. And so it's nearly impossible to do it again in force. Nobody will do it. And so we have to use a lot of stuff which is available, operating system, drivers for all the interfaces. And in some cases, you cannot do it by your own because you get no documentation from vendors. And so it's difficult to bring both together. So in some cases, it's easier to use the layer for the hardware and then using force as a main application. And so you see the concurrence of Python, of JavaScript and other things, even basic.
Not concurrence, competitors.
Mm.
Or would you look at that? Mauser has MRAM in stock. Sorry,
we have
distracted.
also MRAM at Arrow, and especially there are two processors at the moment who has MRAM integrated. For example, Alif has up to 5.5 megabyte MRAM and 30 megabyte SRAM integrated in a chip using Cortex M55 or A32. So it's still a microcontroller, but it's very performant and very good usable even for AI application. And all other MRAM are disappear. And in some cases, new products comes with external HyperRAM, HyperFlash interface. So 8-bit memory interface, which can be used external memory. And for example, at the moment, the fastest microcontroller is i.MX RT from NXP, which runs up to 1 gigahertz with a Cortex M7.
Nice.
Don, I have a question. If you remember when you used NMY products in your robots, what kind of processor you had on those boards?
Oh yeah, that was New Micros. It's a 68HC11 with fourth burned into the ROM. And so I used to buy that 8-bit micro 64K address space from New Micros for $44.
Yes, I know.
Lots of 100.
And in what when was this? In which year?
From 1990 to about 2004. I sold over 2,000 Whiskers robots and other robots, and they all at fourth. And students, the forward 10 feet stop is actual code, and that's why I say that the future programming language is English, and it's going to be built on fourth because fourth allows you to build English language, applications. And a student with zero programming experience in 10 hours would learn about constants, variables, looping on a fun machine. Whiskers actually got mad. He had a temper because it was all behavior based, and the kids used to have a lot of fun making him mad when he's running around. But they wrote their own programs, and they learned the basics of programming in fourth, with this high level language sitting on top of it. I didn't hide fourth. Fourth was there. So everything was a colon definition. That's how they learned programming, was colon definitions. And at the end, they knew all the basics of programming in fourth in 10 hours with no computer science experience.
One thing, heading towards a natural language is, I think, well, natural. But one of the things that Iverson, in his later years, moved from using the terms data and functions and operators. And one of the really important notions, fundamental notions in APLs is operators, and they're so trivial to implement in fourth with the tick symbol. But in any case, Iverson went to, and I use the terms nouns, verbs, and adverbs. An adverb is something like a cross. Okay, multiply across, multiply each. Those are the adverbs. But in any case, that's heading towards that. I mean, I think all of this is sort of a continuum between human language and chip language. But actually, when you think in terms of those three categories, it's interesting how selectors, for instance, something that says, you're in this group, for instance, ends up being a verb rather than a preposition or whatever. The human grammar goes into detail that don't sort of exist when you're composing the sentence.
We need more questions for Chuck or ideas. Who wants to share any ideas about force or uses of force? Rob probably.
Peter, I have a question. but is so broad, it's broad that how the question is this: how can Fort be conceived to be used for quantum computing? I know that is a diversion on what actually is Fort, but I would be interested in thinking how a simple machine can achieve and simulate better a quantum computer that is beyond our capability right now.
I don't understand.
I was thinking about quantum computing and how Fort could be usable.
Oh, I wonder too. I don't know anything about the details of quantum computing. And I'm not really optimistic that it's going to solve any problems. I think Forth would be a good interface to a quantum computer, but I don't know the details.
Neither me, me too. But I was wondering if, because I just know that quantum computing is a very, okay, it deals with different things that we know, but I think that in this moment, actually, in this moment, a qubit is much more a single bit to be used like a gate. So I wonder if using some interface like Fort could be useful. Well, anyway, this is just a wonder.
I think you can use all operating system and languages to work with a quantum computer. As application typical works good if there is any application who need a probability. For example, if you're looking for the best travel away and so on, you can use this quantum computer because the result is looking for all possibilities and then selecting the most of probability. But I think it's not a dedicated application for force. I think more it's using hardware like a small FPGA and extend it with interfaces which can be included in force application. For example, if you realize a motor control or a stepper, then you can use this hardware and the force to combine both to the optimal speed. For example, to give the hardware do 100 steps and the force can calculate the next steps. And so the combination of hardware and software can be better done with force because it's interactive.
One of the best features of ordinary computers is that they give you an exact result. The notion of a computer which gives you probabilities is going to be not really helpful in fields of accounting or even machine control. You don't want, you want precision and predictability and reliability.
Well, about quantum computing, the use case for it really is factoring very large products of two very large prime numbers. I haven't heard of really any other real use cases for it other than that.
I think there are some application like the traveler problem to find the minimal way, but there is other solution who find a nearly perfect solution. So at the moment, quantum computer are more in the security area because there is too many options, and so quantum computer will help. At the moment, it's too less bits who can get, so the solution need a lot of additional calculation and recalculation and organization. So at the moment, it's still the beginning, but it makes problems for the security stuff. So each people who work in this area looking for a solution who can be inert to a quantum computer.
James, you have a question?
Chuck, you mentioned that you switched to subroutine threaded fourth at one point. Do you remember about what time that was? I'm just trying to compare it to when I wrote one for purely ego purposes.
I would guess in the 1970s. Late 70s.
That's way ahead of me. I did mine in the mid 80s.
Okay. Nice try.
Okay, we are slowly approaching the end of the meeting. If someone wants to say final words, go ahead, please. Fitz and Jan did not participate today. They didn't. Fitz, if you want to say anything or.
Let me say thank you to everyone for being here and listening to me and wishing me happy birthday. It's been a pleasure.
Chuck, happy birthday. And thank you for all your contributions. We wouldn't be where we are at right now had it not been for you.
Absolutely. Happy birthday.
Happy birthday. Thank you so much.
Happy birthday, Chuck.
And happy birthday.
I want to hear it in any language.
Happy birthday to you.
Feliz aniversário, Chuck.
Tanti auguri.
Feliz cumpleaños.
Alles Gute zum Geburtstag.
Tillykke med fødselsdagen.
Also finally, Chuck, do you know this board?
Oh, yep.
Yeah. And also there is an RTX 2000 board from the Forstgesellschaft.
Nice.
So they are still here.
Mine is online. Well, behind two firewalls, but still. Yeah, mine is still there. How do I get there? Actually, yes. No, let's see if I can get there from here.
Hey, Chuck, ever work on a personal robot project? A mobile robot?
I programmed a movie camera once, a robot that moved a camera in a predictable path for special effects. That's as close as I've gotten.
Mobile robot.
It was fun. It was hard.
There you go, Jan.
One things about NC 4000, I use this board and he latch up and need more than 2 amperes, but power off, power on, and it's still running. So it's very
nice.
important.
And Rob Probin has a nice robot down there for his picture.
Thank you.
Okay, goodbye to you all.
Goodbye.
See you again sometime.
All right.
Thank you,
bye-bye.
thank you, thank you. You have a nice rest weekend.
I look forward to it.
See you at Fourth Day.
You bet. Thank you
Bye
so
all.
much. Thank you, everybody, for showing up, and you have a nice rest weekend.
Thank you, Cornelius, for organizing.
Anytime, let me know. We know
Bye-bye.
that it
Bye all.
works. Thank you, thank you,
Goodbye.
thank you.
Thank you, Joanne.